Hello everyone, I'm Swadhin, a PhD scholar at School of Earth and Planetary Sciences, Niger, Bhubaneswar, India, and I'm going to talk about the retrieval of sea surface temperature and atmospheric profiles from INSAT-3DR satellite, comparing Bayesian inference, 1D bar, and machine learning. This is the brief outline of my presentation. I'll talk about why it's important, some of the basic principles of satellite remote sensing, the methods I've used in my work, some of the results and future works, as well as a few references. Coming to the question of why it's important, as we know, climate change has greatly affected the surface and atmospheric properties, and to forecast many days into the future, we need to know a global picture of the current atmospheric state. Hence, accurate measurement of these parameters are crucial for weather forecasting and climate application. So, the sea surface temperature measurements, which is one of the most important factor in the air-sea interaction, is essential for understanding and predicting the weather patterns, such as the formation and classification of the tropical cyclones. So the temperature profiles provide us critical information for weather forecasting as they affect the stability of the atmosphere, influencing the cloud formation and precipitation patterns. The atmospheric moisture profiles plays a vital role in understanding the precipitation processes so that we get to know the water budget of our planet. So these measurements enable us to detect the long-term trends and changes in the temperature and moisture. So what exactly do the satellites measure? So the satellites don't measure the temperature, or they don't measure the humidity or ozone or the wind speed or direction. So satellites can only measure the upwelling electromagnetic radiation that reaches the top of the atmosphere. So it measures the radiance that reaches the top of the atmosphere at a given frequency nu. And then the measured radiance is related to the geophysical atmospheric variables by the radiative transfer equation. So the left hand side in this equation shows the radiance measured by the satellite, while the right hand side in the equation shows our description of the atmosphere, which includes the Planck's source term that depends on the temperature of the atmosphere, how much radiation is absorbed in the atmosphere, what was the surface radiation, the reflection, scattering, and the cloud and rain contributions. So now we can tell, given the state of the atmosphere, what is the radiance. So that's our forward problem. So the inverse problem lies is, given the radiance, what is the state of the atmosphere? So that is our question of interest. So we measure the radiance at different wavelengths or channels at the top of the atmosphere, and we try to deduce what could be the ideal state of the atmosphere given the set of the radiances. So measuring the radiances at different channels gives us the flexibility to infer different properties of the atmosphere. If we want to study some of the properties of the atmosphere, then we will choose a channel which probes to the atmosphere. And if we want to study about some of the properties of the surface, then we will choose a channel where the maximum contribution comes from the surface as well. So in a sense, we try to simplify the forward problem in order to simplify the inverse problem as well. This is a brief proposed retrieval methodology for machine learning retrieval. So to train our model for the machine learning retrieval, we have taken the representative data sets that usually occurs in our planet that has the natural variations as well as the extreme conditions. So the ECMWF diverse profile datasets, which give the pressure temperature profile, the moisture profile, the skin temperature in 137 vertical labels were used in this study. So there are 25,000 profiles as such. So we have taken only those profiles which falls inside the INSAT coverage region, and we have masked out the land pixels as well, so that we are only left with those profiles which are only the ocean profiles that falls in the INSAT study region. So we have taken PT profiles, water vapor profiles, sea surface temperature, as well as the latitude and longitude of that particular profile as the input, and we have varied the zenith angle in a zero point 0.1 degree accuracy to capture all the minute variations that happen and that can contribute towards the change in the brightness temperature. So we have generated a data set of around 5.1 million profiles as such, and we have used RTTOV, that's a fast 1D radiative transfer model. So that simulates the satellite radiances given a set of surface and atmospheric conditions. So the RTTOV simulated brightness temperatures as well as all the surface and atmospheric conditions were given as an input to the machine learning model. So the model was trained based on that. So the trained data sets were divided, entire data sets were divided into the training data sets and test data sets. So the model was trained based on that. So whenever we have an INSAT 3D observed brightness temperature after applying a cloud mask and the bias correction, so we can say what is the PT profile, water vapor profile, as well as SS. This figure shows the generation of the lookup table that was used in the machine learning retrieval as well as our 1D VAR approach. So the left hand side figure shows the pressure temperature profiles that we have taken. So these are the more than 5.1 million profiles. On the right hand side figure shows the water vapor profiles that has been used in the study, and the onset figure that shows the location of all those profiles. As you can see, these profiles are supposed to cover all the INSAT coverage region. So we have done two types of studies. One is the combined model and one is the separate model. So the combined model tried to predict 274 target variables from the 20 featured input, and the separate models tried to predict 137 target variables from the 20 featured inputs for pressure, temperature and water vapor separately. As you can see, for the pressure temperature profile, the combined model performed well. So it has a low mean square error and a good R square score. Whereas for the water vapor, the separate profiles perform. So these are some of the results. So as you can see, the sea surface temperature that we have obtained from the lookup table, it matches very well with the ERA 5 reanalysis data. So we have developed a novel joint retrieval algorithm for INSAT-3DR to retrieve the temperature, structure, humidity and SST, which is distinct from the existing operational methods. We have generated an extensive lookup table of over 5.1 million profiles, incorporating the minor zenith angle variations, and during benchmarking, we observed strong agreement between the temperature, water vapor profiles and SST derived from the lookup table and machine learning, as well as the radiation and observations and the ERA 5 data. Thank you for your attention.